Have you ever heard someone describe themselves as left-brained or right-brained? That might sound like, oh, you should let me do the math. I'm very left-brained. Or, you can tell I'm right-brained because I love art class so much. When in the 1960s, this idea of particular tasks being associated with one side of the brain or another started to become widespread. Analytical or logical tasks were associated with the left side, while creative or emotional tasks were associated with the right. If you were great at one of these sets of tasks, that meant that side of your brain was dominant, leading it to become a defining personality feature for some people. In case you doubted at how ingrained this idea has become in our society, a simple search for a brain icon in a very popular set of software suite yields this as one of the first results. Since that time, studies have been conducted with participants doing a wide variety of activities while undergoing a brain scan. Regardless of the kind of activity, multiple areas of the brain were lit up on both hemispheres of the brain, showing that most activities are actually global rather than specific to one side or another. While this may seem like a relatively harmless trope, a silly idea, it still contributes to the idea that analytical logical skills, or those of a scientist, are completely separate from the creative and visual skills of an artist, leading to this idea that they're two distinct fields. Not only is this harmful for recruitment, especially at a time when science and engineering fields are trying to bring in a wide variety of diverse, out-of-the-box thinkers, but it is decidedly not true. Not only are these fields similar in terms of the content, but they're also similar in terms of the skills that are needed to be successful in them. To highlight that, let's zoom in on a very common part of most art supplies, pigment. Pigment is what gives art supplies their color. Watercolor, crayons, oils, these are all combinations of pigment with some kind of binder, like a wax or oil. But why do they appear to be different colors? Well, when white light hits a material, like a red piece of paper, red light is reflected, meaning that object is red. But why does the white light become red? Well, white light is actually made up of all of the visible colors, and even some that we can't see. So when the white light hits the paper, only red is reflected, meaning the other colors are absorbed. This is what happens if you've ever gotten into your car in the middle of the summer and that black seat gets pretty darn hot. That's because it's absorbing all of the colors of light from the sun. But why does that mean it gets hot? You can tell I was that kind of kid growing up. Well, when it comes to light, color is related to the amount of energy that is in that bit of light. And so when we're talking about color absorption, really we're talking about energy absorption. The car seat is getting hot because it's absorbing a lot of energy. That energy absorption is happening on an atomic scale by the electrons that exist in the atom or by creating vibrations between neighboring atoms and molecules. So the colors that end up absorbed and creating those vibrations are dependent on the elements that make up that particular pigment and also how they're bonded together. For example, a very common pigment color is alizarin crimson. It gives us this kind of orangey red shade. Well, this pigment is actually made up of a combination of hydrogen, oxygen, and carbon atoms in this particular configuration. If we were to break up our white light into the individual colors or wavelengths and measure their reflection at each of those individual colors, alizarin crimson would produce a curve that looks something like this. What we would see is a high amount of reflection in the red or orange colors and low reflection everywhere else. This is the signature of alizarin crimson, its spectrum, which means that this particular curve would change depending on the pigment that we're looking at. Artists and scientists have used this property, this independent signature for all of the pigments, as a way to analyze art, to identify what paintings are actually made of, and help to figure out how to restore those paintings. This technique is called spectroscopy. And while it is very common now, artists have been producing art long before this technique was available. Those artists are all early scientists, experimenting with pigments and varnishes and binders, experimenting and failing over again and trying again and again. Their work was peer-reviewed in galleries and museums and over the test of time. The idea that knowledge has to be written down in order to be science is a relatively Western idea, one that minimizes the importance of oral traditions and the sharing of experiences. And yet, if you talk to most science graduate students, they'll tell you that they learned the most sitting in lab with their senior students and scientists and listening and learning and experimenting side by side. The scientific peer review process and the resilience required to grow from that whole process is not that dissimilar from the critiques that happen in art classes every day. The closer we look, the more similarities we find. With color, what dictates the color that is reflected can also tell us what color is produced when that material is given enough energy to do so. These are examples of plasmas, very energetic ionized gases that are used commonly in the semiconductor industry to either create thin films or etch them away. The color that is produced depends on the kind of gas that we use to make the plasma in the first place. And its intensity depends on how much power we pour into it. We can use this as an early indication of if our process is working in the way that we expect it to, or if something has gone a little awry. But because all of these things are signatures according to the elements that we are using, it helps us to identify what went wrong and move on from that. But elemental makeup is not the only way we can produce color in different materials. To look at another way we can manipulate color, we have to talk about another very serious art supply, glitter. You might think that this is just a silly craft supply for children, but it's actually a highly engineered product that is designed not only to reflect light, but to reflect it in a specific way. Single color glitter is very different from color shifting glitter. Just like pigment, glitter reflects light, and the color that we see, the color that's reflected, is the color that it looks like, right? But unlike pigment, glitter takes advantage of not just light as a chunk of energy, but also light as a wave. That's right, light behaves as both a particle and a wave. And like a wave in a wave pool at the water park, light waves can overlap and combine together, creating bright spots and dark spots. We call this interference. By carefully designing our layers, we can create constructive interference that creates a color that is reflected that we wouldn't have otherwise expected. Even when we keep the materials exactly the same, and the only thing that we change is the thickness of our layers, we can create a very dramatic difference in all of the colors that we see from our sample. And then if we look at that sample from a different angle, the color shifts even further, because now the light has to take a longer path through the film before it reaches your eye. This is how color shifting glitter works, but it's also the technology used for Bragg reflectors in fiber optic communications. The scattering that creates these colors can also happen off of small structures. This is an image of camera pixels that are about 5 microns wide, which, if you don't know what a micron is, that means these things, you can stack about 15 of them side by side in the width of one of the hairs of your head. So they're pretty small. But yet light is actually smaller. So the colors of the light are related to the wavelength of that light, meaning the distance from the peak of one wave to the peak of the next wave. And so when the different colors of light see these edges, they bounce off slightly differently and scatter in different ways. And so they scatter in a way that produces a rainbow. As someone who very frequently makes things that are much too small to see with your naked eye, this rainbow is often the first evidence that I have that a process actually worked. All visual art is an interaction between light and materials, a vivid display of quantum physics in action. But this isn't just a one-way relationship. Art contributes to science too. In 2014, Surrey Nanosystems developed an ultra-black material called VantaBlack that is capable of absorbing over 99% of the light that hits it. Originally, this was intended for sensing systems, for reducing straight light in those optical systems. But it caused quite a stir when the company decided to exclusively license this material to only one artist for use. What was missing from a lot of the ensuing commentary is that this material was based off of carbon nanotubes. You remember those plasmas from before? Well, plasmas are used to create carbon nanotubes, meaning the materials that you can deposit them on and how much can be produced at a given time is very restricted. Even so, this controversy fueled innovation, leading other artists to create their own materials that could be more easily manufactured and produced and spread. Even the company that produced VantaBlack ended up making a spray-coated version rather than a plasma-coated version. Another way art pushes science forward is a way you've probably interacted with a little bit more, which is from the movie theaters. Right? We've all seen movies that have used computer-generated imagery to enhance the pictures or take us away to a different world. A good example of this is from the movie Interstellar, where we travel millions of light years away to see what a black hole looks like. While it may seem like this is just an abstraction and artists' imaginative idea of what a black hole may look like, the movie studio actually brought on a physicist to calculate from first principles what light would look like bouncing off of the mass, circling around as a black hole before it gets pulled in. This calculation ended up so accurate that it correctly predicted what a black hole looks like, which was further supported several years later when we got the first image of a black hole millions of light years away. Beyond that, scientists can also just like art too. Especially with the invention of smartphones, we can capture the everyday beauty of the work that we do. We can find ways to show off the things that we can make or how small we can make them. If you have to make a shape, why not make it an interesting one? When IBM created a technique for picking up an individual atom and moving it over to a side of a sample before freezing it in place, they could have just taken a static image and called it a day. But instead, they created a series of images, creating a stop-motion film. A boy and his atom still holds the world's record for smallest stop-motion animation. And I don't mean in terms of length of the movie, but in the size of the frames. Nano art like this is a great way to benchmark new technologies and show off what we can do. Like with this image, where the scientists took an actual painting, boiled it down to pixels, and then created those pixels in the space about the size of a hair without using any pigments at all. Creating a combination between science and art allows us to get energized, to get excited for the science. It allows people to see how that science can actually be used. Remember that spectroscopy that I mentioned before? Well, it is a technique that's commonly used by astronomers to determine what elements exist in stars and atoms and nebula millions of miles away. Some artists, like Dr. Lacey Brock, produces multispectral art, which combines all of this data in a way that we can understand a little bit better. Because when these astronomers take data, they're not just looking at visible light. They're looking at the invisible, the infrared, the ultraviolet. And by laying these images on top of each other in a way that we can see, it gives us a closer insight to the world around us, the universe around us. Art gives us a way to express abstract concepts, but it also gives us a way to tie the past to the present. Artist Sarah Rosalina does this really well as she combines textile techniques and beadwork techniques passed down from her family with recent discoveries like the cosmic microwave background radiation, and even incorporates AI and 3D printing into her work. Things like this allow us not only a form of self-expression, but also a way to forge a self-identity and a sense of belonging in fields that may have historically kept us out. Self-identity as a scientist is linked to whether or not we are successful in science and math, but it's also linked to whether or not the people around us say, you know, you'd be a good scientist. So if there's a budding artist in your life, be sure to tell them that their attention to detail and ability to think critically about the world means that they would make a great scientist. And if you ever doubt that science is art, I would encourage you to just look to the stars. Thank you.